Our free response question of the day. So this is the actual question that was used a year ago in 2019. Question number 6, we're going to answer it together. And again, there's not much room on here to answer it. If there is room, I'll answer it on there. If not, for the most part, I'm going to answer it on a separate piece of paper. So we have three functions, f, g, and h. They both are twice differentiable. That means they're continuous, and you can take the derivative everywhere. And it says g at 2 equals h at 2, which equals 4. The line y equals that is tangent to both the graph of g at x equals 2 and the graph of h at x equals 2. So first of all, it says find the derivative at 2. Well, if I have the tangent line and I want to find the derivative, all I need to know is what's the slope of the tangent line. So because the slope of the tangent line is the derivative, that's all you need, and the answer is 2/3. I know, right? If you know what you're looking for. So the slope of the tangent line is a definition of derivative. What's the derivative of h? Well, that's the tangent line. What's the slope of that tangent line? What does m equal in that equation? 2/3, and it's over. Let a be the function given by that. Write an expression for the derivative of a and then find it at 2. So do you understand the power and product rule here to help you out? So I'm going to do that over here. So just say at 6a is 2/3 was super simple, hopefully. B, you're given a at x equals 3x cubed times h at x. So what's the derivative of that? Can you do the product rule? So that's the first times the derivative of the second. You know you can always press pause, try it first, and see if you got it right, and then you can press play, or you can work with me. Plus the second times the derivative of the first, it's 27x squared. Right? No, 3 times 3 is not 27. That's 9x squared. Thank you. Then it says to plug in. So first of all, that's done. And then it says find the derivative at 2. So wherever there's an x, plug in 2. Now, the only thing you have to simplify here, you actually don't need to simplify this part, but what's the derivative at 2? We just did h derivative, that's 2/3, so plug that in. What's h at 2? It actually is also given in the question, that h at 2 equals, there, h at 2 equals 4, so we're just going to put in 4. That's it. And then plug in 9, and then 2 squared. That's a beautiful answer. See, again, there's no need for simplification, and there's not a multiple choice one for 2020. So for free response, all practice, practice, practice. That once you get there, you let it go. Part C, you're given a function. Let me write it down. H at x equals x squared subtract 4, 1 subtract 5x cubed, and x can equal 2. And then it's known that the limit as x approaches x cubed can be evaluated using L'Hopital's rule. So this must mean that it's indeterminate. And if it's indeterminate, that means we already know x must equal 2, because then it's 0 over 0 for it to be indeterminate. So it's known that you could do that. It says use the limit as x approaches 2 to find f at 2, and so on. So if that's true, then x squared minus 2 must equal 0. So when I solve this, x could either equal positive or negative 2. Now, if I can use L'Hopital's rule, it's not asking for what x equals. I told the x is 2, right? F of 2. That we're doing L'Hopital's rule is the derivative. So if I want to know the limit as x approaches 2 of h at x, then I can take the derivative of the top, that's 2x, derivative of negative 4 is 0, derivative of 1 is 0. Then I'm going to do the power rule. And then I'm going to do it one more time. So we have the negative here. So 3 times negative is negative 3. And then subtract 1 from the exponent. Oh, and it also needs a hook of f prime at x. I'm going to do this and substitute in now. So now I can substitute in 2. So what is the value? Now that you know you can substitute it in. Before we couldn't plug in 2 the way it looked. That's why we need L'Hopital's rule. But now I can plug in 2 in terms of what's happening. So again, before plugging in 2 would lead to something indeterminate. That's why I couldn't do it before. So I took the derivative. Now I can plug in 2. That's 4, obviously, on top. Negative 3. What's f at 2? It says f at... don't know f at 2. Do I? Don't know f at 2? So do we know f at 2 equals 1? Well, let's go back here. Some fancy-dancy stuff. Because L'Hopital's rule, we know that the limit as x approaches 2 of x squared minus 4 must equal 0. Therefore, the limit as x approaches 2 of 1 minus f at x all cubed must also equal 0 for it to be indeterminate. If that's true, when I plug 2 in, what would make it 0? F at 2, therefore, must equal 1. Because when I plug in 2, f at 2 must be 1, so that 1 take away 1 is 0, so that f at 2 equals 1. There you go. Let's come back here. Now, what's the derivative at 2? Well, I don't know the derivative at 2. So what else do I then know? Does it say it equals 4? It is known that can be evaluated. So I'm looking on the answer key and saying it's equal to 4. So then the question is, why is it equal? So they're saying this is equal to 4. So, oh, it's because in the question it says the derivative at f. Can I say that? Is the derivative for f at 2 equal to 4? Oh, the derivative at 2. Is 2/3, right? Let me back up here. Make sure I know what I'm doing, or not know what I'm doing. The limit as x approaches that. So all right, so the limit, if you substitute in, as x approaches 2 is the same as h at 2. And we're told that h at 2 equals 4. So when it talks about the limit as x approaches 2 for h at x, that's just a substitution question, which would be the same as h at 2. And we're told that h at 2 equals 4. So this is equal to 4. Oof, finally got there. Then, if I want to answer that, and understand that's 4 over 1, so the numerators actually match. If you take the denominators to figure this out, divide by negative 3, and you actually get f prime at 2 equal to negative 1/3. Wow, right? There's a lot of thinking jinking going on there. So one question is, what is the derivative at 2 equal? That's negative 1/3. What is f at 2 equal? That is positive 1. So we got there. Somehow we got there. Let me recap how we got there. So you're given what h at x equals. And you're told that L'Hopital's rule works here, which means the numerator must be equal to 0. And if you solve that, the numerator equal to 0 and plug in, and the denominator equal to 0 and plug in, f at 2 then must equal 1 for this to be L'Hopital's rule. I think that's fine. This one here, we got to make sure that when we do L'Hopital's rule, we do the derivative properly. So that's 2x. The challenge was the denominator. So we have to do the chain rule here. So 3 times negative 1. And then what's inside the hook we need to include, which is the derivative of the base. Then we need to understand that when you take the limit as x approaches 2 of h at x, that's the same as plugging in 2. And we know h at 2 equals 4. So then we can take that expression for the limit and make it equal to 4. Then the numerators are equal, so just take the denominators, make them equal to each other, and get that f, the derivative of f at 2 by itself, and you get the answer. Boy, right? But you stuck with me, so I'm proud of you. Part D. It is known that g at x is less than or equal to h at x between 1 and 3. Let k be a function satisfying this. So g at x and k is sandwiched in between here, sandwiched between g and h from 1 to 3. So for every value between 1 and 3, k is always in between the two. Is k continuous at x equals 2? So what do we need to know for that? Continuous means like differentiable helps, right? So g at x and h at x are both differentiable. That's what it says in the question. And continuous, because if they're differentiable, that means they are continuous. So the limit as x approaches 2 of g at x, so we're talking about 2 here, is the same as just plugging in 2. And if I just plug in 2 in the question, it says the answer is 4. If I do the same thing for h and plug it in, same thing, plug in 2 for h, you get the same answer 4. That's from the question. Now, this is a unique theorem. It's called the squeeze theorem. So, because of the squeeze theorem, so that's a unique little theorem, k at x is between g at x and h at x for all 1 through 3. The limit as x approaches 2 for k at x, which is k at 2, is going to equal the same as that, because it's squeezed between the two. So if at all functions, it's squeezed always in between the two functions, that equals 2 part, that at that value 2, g and h are equal to each other because k is squeezed in between, it is also equal to 4, and therefore at x equals 2, k at x is continuous. That was it. So this is a unique theorem where you have two functions and one that is squeezed in the middle between the two of them. And if we have the same limit on one side and the same limit on the other side, the theorem says that what's squeezed in between them would equal the same answer. And if the limit exists there, and it's there, it's therefore going to be continuous because of that. Because there's a value there, and it's equal to 4. So it's continuous there. All right. Enough, right? I'm proud of you. We got to the end of this. Mr. G Math. Over and out.